Hi, everybody. Thanks. It's great to be back at YOW. Last time I was here was 2012 with Eric talking about RX. Today I have a new treat for you. This is a synthesis of Kalman filtering. And are there some engineers in the audience who are familiar with Kalman filtering? May I see hands? That's good. And of functional folding. Are there some SDEs in the audience who are acquainted with functional folding? Can I just fold in general? Oh, good. That gives me some direction on where to emphasize things. Okay, so the point of this synthesis is the following. They say that if you have a hammer, everything looks like a nail. Well, I have a hammer and a screwdriver. So to me, everything looks like a hammer or a screw or both. So you see how having two tools makes you 3 times more powerful. Kalman filtering is one of the greatest inventions in human history, really. It enabled the entire space program. It's the original form of machine learning. It's distinct from current methods of machine learning in that you have to have a model to take advantage of Kalman filtering. But what you get in return for doing the hard math of building up a model is you get amazing speed, and the thing runs in constant memory. When I was at Jet Propulsion Lab, we had a single Kalman filter for the entire solar system. That's 15,000 asteroids, every planet, every moon. In those days, it was only 175,000 states. Nowadays, it's over 250,000 states in one vector. Just imagine one giant vector. In those days, we ran it on a 1 megabyte computer that cost $1 million. So we had 15,000 lines of grotesque Fortran code, almost all of which was doing data swapping. So we could pull in little bits of these matrices and vectors, and 4 or 5 lines of which was actually computing the answers. One of the things that I want to show you is how you can turn this around, the spacecraft tracking problem. You know, we're using observations to track the positions and velocities of every object in the solar system. But you can turn this around with a simple transformation and estimate the position of the telescopes instead. If you can Kalman filtering lets you pretend that you know some things. And then you can if you pretend you know some things, then you solve for the other things. I'll show you exactly how this works. Well, if you pretend you know where the planets are, then you can solve for the positions of the telescopes, and you can directly see tectonic drift on an oscilloscope. It's absolutely bone-chilling, hair-raising, and it's one of the things that made me fall in love with this topic forever. So now I'm working in robotics and drones, and I get to use it again. But after years in functional programming, I discovered that this fits with a functional fold. And this gives you a screwdriver. One of the difficulties with numerical code like Kalman filtering is that they can be difficult to tune, especially if you have a wide dynamic range in your floating point number. So let's think about the spacecraft tracking problem for a minute. We know the position of the centroid of Saturn to within 50 meters, 75 meters or so, but we don't know its distance to within 100,000 kilometers. So this means your covariance matrices are incredibly long, thin needles and you square these numbers and add them up, and it's a big mess. So what do you want to do to beat this problem? You want to test this code in a friendly environment where you have repeatable data in memory, debuggers, visualizers, all of your tools at hand, and then you want to deploy it without even recompiling it into the embedded system. And functional fold is exactly the thing that lets you do that, because you build all of your data processing code into a mere function. Fold lets you apply that function over any sequence of data. What fold does is abstract iteration over sequential data. So that means you take your single function that you've built and tested, you run it over arrays in memory and make sure it's all working. You can run it over data distributed in time. Asynchronous. So this is the message of RX, if any of you remember that. You take exactly the same query code that you can run over objects in memory, and you can run it over asynchronous data streams and other kinds of abstract iterables. So let me get into this. First, let me just jump straight to an example. to motivate what Kalman filtering does for you. Let me blow this up a bit. Now here I have a little tiny Kalman filter running. It's running in constant memory. Every time I move one of these gadgets, it resets and starts over, taking data. Let me tell you what's going on here. This is a 2D simulation of spacecraft tracking. The little stations down at the bottom are taking nothing but angular data. They're looking at the spacecraft that you're trying to track, which is in the center of the crosshairs, and you see they're jumping around because there's noise in the system. So all I'm taking are angles, and I'm trying to estimate a position. This is the recurring theme in Kalman filtering. You have something, you have some data, and you want something else, which is hidden state variables. So from angles, that's what I have. From noisy angles, I want the position of the spacecraft. Now the model, remember I said that Kalman filtering is a kind of machine learning where you have to have a model ahead of time. The model goes in the opposite direction. If I knew the position of the spacecraft, then it would be easy to calculate the angles. This is an exercise in school geometry. And in fact, those are the blue lines there. So what Kalman filtering is doing is statistical function inversion. If I knew the state, I could get the angles. I don't know the state. I have the angles with noise, and I want the state. In fact, it's nothing but an extension or a reformulation of least squares. That's why it's called optimal. Kalman filtering is optimal estimation of the state given the noisy angles. You remember least squares from school where you plot the height of people versus their age, and you've got these noisy little dots and you draw a line? What are you doing? You're estimating parameters of the line. The line is the slope and the intercept. And how are you doing it? You're doing it in such a way that the square error is minimized. This is exactly what's happening here, only in a different, bigger context. And I'll show you several deeper examples. What I have are these noisy observations. I keep accumulating them over time. You notice this thing is not going to blue screen. Oh my God, I can't believe I said that. It probably will. But it runs in constant memory. And this was necessary for the space program. You have tiny computers with 16 kilobytes in them, and you're going to try to estimate the position of the moon while you fly the Apollo spacecraft to it. I wasn't overstating it when I said it's one of the greatest inventions in human history. Professor Kalman won the Draper Award, which is the engineering equivalent of the Nobel Prize for this invention. Just a couple of other features that we'll get back to. And you see how, you see that ellipse? That ellipse is the current estimate of the uncertainty in the position. So when I move any of the stations, I reset the data stream, and as the angles accumulate, that ellipse gets smaller and smaller and smaller. And I'll show you exactly the subtraction expression that does this. And notice also that if I line up the stations, I don't have a lot of cross-track information. I have lots of, what do they call it, downrange. I don't have a lot of cross-range information. So the error ellipsoid is very thin in that direction. And notice the crosshair doesn't really find the ground truth. The ground truth is the little dot where the blue lines intersect. It's actually quite bad there. If I leave it running overnight, it might get enough information to correct it. But so this is what I meant by tuning. If you don't have enough information, the Kalman filter, of course, it's garbage in, garbage out. It won't give you stuff. Let's do some more observations. This is that example. Here are some other applications. In drones, we have two instruments on board. We have a GPS that's trying to tell us the altitude, and we have a barometer that's trying to tell us the altitude. What do we want? The altitude. We don't know it. We have noisy observations from the GPS and from the barometer. If we knew the altitude, then we could predict the output of the GPS and the barometer. It's a long, involved model. But we statistically invert it. We take the noisy output of the GPS and the barometer, and we get an estimate of the unknown state. How about this one? This is a very important problem nowadays. batteries. Lithium-ion batteries, they don't like to be discharged too much, and they don't like to be discharged too fast. In order to tailor the application to the battery, you have to know the charge in the battery. But you don't have that. You can only observe the voltage. If you knew the voltage, you could predict the charge. You want the charge, and you have noisy measurements of the voltage. So you statistically invert. You have voltage and want charge, but the model goes the other way. If you had the charge, write down the physics equation to predict the voltage. There are probably 50 Kalman filters in your smartphone. The GPS, the accelerometer. How does it know the pose of the phone from the GPS and the accelerometer? It's Kalman filtering. How does it know when to warn you to turn off your Wi-Fi so you don't burn the battery down? There's a Kalman filter in there that does this, exactly this computation of charge from voltage, from observed voltage. Here's another one, tectonic drift. I told you about this. In forward operation, we pretend we know where the scopes are, and we take data on the position. We take angle data and ranging data to the objects in the solar system, or you turn it around and predict the positions of the telescopes. More examples from the business world. Economists routinely use Kalman filters. Sometimes they don't call them that. But here's a case where you want recommendations, but you can only observe purchases. If you knew the recommendations, you could predict the purchases. So the hidden state variables are the recommendations that you want to solve for. So you start with some a priori recommendations, you observe the purchases, you get better recommendations. You want the shipping rate and a what do they call this, fulfillment supply chain. You want to know this theoretical capacity of your supply chain, but you can only observe shipping rate. You have a model that goes the other way. If you knew the shipping rate, you could predict the capacity. If you knew the capacity, you could predict the shipping rate. You observe the shipping rate and solve for the capacity. You want supply and demand, but you have prices. You want allocations in your accounting, and you have expenses. You want images, you want a world map and you have images. This is the SLAM problem, simultaneous location and mapping, common in robotics. In general, you have signals and you want some models of the sources. And they all look like this. You have some states that you want for your models, and you have some observations. So you iterate a function from state estimate and observation to new state estimate. You just keep iterating this function. Well, that's fold. Fold abstracts iteration. So now we get deep magic. Here comes the hammer, here comes the screwdriver. They all look like this. There's some function. You put in an observation on the left and a current state on the top, and you get a new estimate of the state. Except they recycle the states. Boom. Take the old state, put it in the top, new observation in on the left, and we're going to get a new state. And we just keep cycling this around. So as you saw, the little angles are going tut, 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 and I'm getting better and better estimates of the state. I'll show you that in the next cartoon. But the thing to note is the function that's doing the data processing is completely decoupled from the mechanism of delivering the data. The mechanism of delivering the data is symbolized by the outer bottle. You can look in there and see the states at any time you like. So in the case of Kalman filtering, the state comes along with an ellipse, and the observation comes along with this model. So the observation is some particular angle. The model A is a guy that takes the state and predicts the angle. So the A, I didn't show the little state ellipse and crosshairs goes into the Gazenta pipe of A, and out comes a prediction for the angle. You subtract it from the actual observation, and that's just like the least squares, where you put the height versus the age. So that big box is fold. What I'm going to do, I'm going to run through this because I'd rather show you some real code working. But remember I said that the Kalman filter is a mechanization of least squares. It's also a generalization of the running mean and the running standard deviation. It is possible to compute the running mean in constant memory, and I'm sure you can see how that would be. In fact, I'll show it to you. This is running count. I want to skip over that. Let me show you running count here. On the left, we have a more or less standard imperative way of writing that. And on the right, we have a way of computing the running count as a functional fold. The imperative way on the left creates a local variable called Z0, sets its initial value to 0, and then defines two functions named accum and peak count. Those functions are defined in the global namespace. So if you're familiar with a pattern in Lisp called let over lambda, this is a let over lambda. It's also just a way of encapsulating a local variable. It's quite similar to a singleton object pattern. So I call after that, because I don't have types, if those of you who saw Tony's talk, he doesn't need unit tests because he has types, but I don't have types, I need unit tests. So there's my unit test. I accumulate 1, 2, and 42, and since I'm only counting, I get 3. 3 is down at the bottom. Oops. Okay, so now we see the parts. That's kind of yucky over there to do it in this imperative way. In the functional way, I don't have to have all this machinery. I don't need a hidden variable, Z0. I just need a function. So the top line in fold is a binary function from a state and an observation to a new state. So just keep repeating this to yourself. Anytime you have a function from a binary function, takes two inputs, a state and an observation, gives you a new state, you're a candidate for fold. The second line on the right-hand side is the initial value for the state, 0. I don't know anything, I'll just say 0. And then this particular fold works over a list. I have a concrete list, and it gives me the same answer. Now, what I want to do is jump toward a deeper example. So this is an experiment. I want you to yell if what I'm saying is not clear. I'm insisting. The purpose of this talk is to get the ideas from my head into your head, and if something I say isn't clear, I want you to stop me, and I'll make it clear. So what I'm going to do here, I know I'm scanning past a lot of stuff. This won't be so bad in a second. There it is. There's the celestial beauty, you know. As Bruce Lee said, don't take your eyes off the moon or you miss all the heavenly beauty. This is the entire Kalman filter. Right there, the yellow stuff. All the rest is ceremonial noise to plot and do all kinds of things. Okay. The problem that I want to walk you through is the problem of estimating the parameters of a cubic polynomial. I'm going to get there. Here we go. This is my ground truth. These are the 4 coefficients of a cubic polynomial. I'm going to generate some noisy observations starting from this ground truth. The model looks like this row, t cubed, t squared, t, and 1. If I multiply that model by, if I do a vector multiply of that model times an estimate of the state, then I will get a predicted observation. Here it is symbolically. Here's the model at any time t. This isn't time, as I will show you. It's just the independent variable of the polynomial times the ground truth. And sure enough, there I get minus 5t cubed minus 4t squared plus 9t minus 3. I'm going to fake some data. And anything that I skim over is unimportant. So this is what the fake data looks like. Here are a bunch of times from minus 2 to 2. Here are a bunch of rows. I just evaluate that A row. For each one of those times, it's t cubed, t squared, t to the power 1, t to the power 0. Power 0, it's 1s all the way down. Here's the true z. which I calculate from the ground truth. And here are the z, or z, which are my simulated observations. I just add some noise to make that a column of z. So I'm first going to do a Kalman filter on this and try to figure out what I'm going to pretend I don't know the coefficients of the polynomial and try to find out what they are. But first, let's plot them. The clean line is the ground truth. The dots are the noisy observations. We can do this with batch least squares and whatnot. Or we can, yes. So let me show you the batch least squares, and I'll go back to this in a second on the other slides. If I do batch least squares, some of you may remember this formula: ATA inverse times ATZ. That gives you the least squares estimate over all the data. So we're not Kalman filtering yet. We have all the data. Kalman filtering, we do it one at a time. So I'll show you that. And it's not bad. The result I get is -5, -3, 9.6, and -3. And the truth is -5 exact, -4 exact, 9, and -3 exact. But this gives me something I can compare my Kalman filter to. So now we're going to do this incrementally. I'm going to run my data through the Kalman filter. I do not know the coefficients. So I begin with zeros. Another way of expressing that I don't know them is the covariance matrix. I put in an expression of my uncertainty in those zeros, and I put it very large, 400 along the diagonal. I don't know anything. I picked 400 because it makes the plots look nice. So there's my Kalman filter, which I'm going to show you some features of it in a minute. And I run it through, and I get exactly the same. When I'm done, all the way down at the bottom, line by line, I get exactly the same x's as I got before. So now I believe that the Kalman filter is delivering the least squares answer. Let's look at some of this. Let's look at this beautiful expression here. Here I'm doing fold list of this function update. The function update is the one I showed you above, which is applying the Kalman equations to this a priori matrix that I showed you before, zeros and 400s. I don't know anything to start with, and partials and observations from my experiment. This is the entire expression of the whole thing. We do it over and over and over again. So that's showing you fold. Let's look at what it looks like. So as I increment this u, I'm going to be adding my data one at a time, and I'm executing the same Kalman filter that I had above. The blue line is the ground truth, and the orange stuff is my current estimate. Well, I don't know anything at all, so my current estimate is completely messy. It doesn't tell me much. I add one data point, and it's already beginning to figure out that the cubic, the real cubic, is somewhere in that orange area. I add more data, it gets closer, gets a little further away, gets a little further away again, starts coming back, and as I keep adding data, the Kalman filter eventually figures out exactly what it is. It's actually quite nice to scramble the data. I made the point above that t here is not actual time. We're estimating static parameters, x0, x1, x2, x3. So this is not time, it's just the independent variable. And this time I'm going to add the points in random order. And you see right away, because they're spread out all over the place, I start getting better estimates right away. It's sometimes quite handy to scramble the data when you're doing this kind of data processing. Okay, a couple of more points. Remember I said if I pretend I know one of the parameters, then I can solve for the others. How do I pretend I know one of the parameters? All I do is change the a priori. I'm not changing the fold. I'm not changing the filter. I just change the data. So in this case, I pretend I know the coefficient of the square. It's 9. And I pretend I put in an a priori value for it, and I put in an a priori covariance of 0. This means Kalman filter, don't estimate the parameter. I know what it is. My covariance, my uncertainty in it is 0. Large covariance means large uncertainty. Small covariance means small uncertainty. Now, what does that look like? Now, in this plot, I'm not going to add the points one at a time. I'm just going to show you the final answer. So when I think that that parameter 9 is actually 9, the ground truth, I get really good results. But if I make a mistake and I say I think that parameter is -4, the Kalman filter not only blindly solves for a cubic, but it solves for the wrong one and tells me that its uncertainty in the answer is very small. That's what it's all squeezed in together there. So don't lie to your Kalman filter. If you pretend you know where the satellites are, so when in the satellite tracking world, what we do is we have geodetic markers on the ground, and then we have this giant 60-meter telescope that's tied to this geodetic marker, and that tells us where all the spacecraft are. We turn the problem around and we say, well, that geodetic marker in Hawaii is moving with respect to the geodetic marker in Massachusetts. So I add some covariance. How much? Just enough. And by God, you can see a tectonic drift on an oscilloscope, 3 centimeters a year. Hawaii is moving away from Massachusetts at the rate of 3 centimeters a year. Okay, back to the talk here. This is how you do, oh yeah, a few more folds. Let's say your initial state is 0 and 1, and we're going to give some names to these. This is off of Kalman filtering. This is now about folding. That's the screwdriver. The hammer and the screwdriver go together really well because they give you the ability to test your code in a friendly environment and then deploy it in a harsh environment. But the screwdriver works all by itself too. My states are pairs. The name of the first slot in the pair is called last. The name of the second slot in a pair is called current. And to update the state, don't really update, we compute new ones. That's functional programming. Everything's immutable. But what we do is a binary function there. Given a state and an observation, notice the right-hand side of the little arrow. That's the body of the function. I'm going to ignore the observation. I don't care. I'm just using it as a ticker to move me one step at a time. I'm going to take the old current and put it in the new last. And I'm going to take the old current plus the old last and put it in the new current. And of course, that's the Fibonacci sequence. I gave the joke away already by giving this function a name, Fibonacci combiner. But we get to put it in a fold. I just put that function with an initial state of 0 and 1, and then the nextables in this case is just a list of 9 numbers. It doesn't matter what they are because the function ignores them. Why not any binary function? In fact, any binary function works out. It turns out that there's a little matrix 0, 1, 1, 1 that if sequentially multiplied by itself or raised to a matrix power yields the Fibonacci numbers in the second row. So let me talk a bit about folding over arbitrary sequential data. We've seen now that any fold, and you Haskellers will know this as scan, but I'm finessing the difference between folding and scanning because I always want the intermediate results in the case of Kalman filter. The difference between folding and scanning is that fold gives you just the final answer, and scan gives you all the intermediate steps, which is what I want. Remember the blue box. I always want all the intermediate steps. I can write a fold over a list. And Haskell type notation here, fold list is a function that takes a binary function, an initial state, and a list, and gives you a new list. So that's what we're doing with this matrix multiply here for Fibonacci. Binary function, matrix multiply, 2 matrices, binary, boom, get a new matrix. Observation, state, state. Initial state, just my base matrix, and then a repetition of that matrix 9 times. That's a fold list. How about fold stream? A stream is an abstraction for infinite data. So it's kind of halfway between lists in memory and asynchronous data coming in on the wire. Typically, they're represented as a pair of a value and a function. And if you evaluate the function, you get the next stream. So it looks just like a cons list, where it's a cons of a value and a cons. And if you evaluate the cons, but it's lazy, because the cons is not realized in memory. It's a function. You have to actually call the function. The signature of fold stream is exactly the same as the signature of fold list. Binary function, initial state, stream, get a new stream. Here is, this is a little bit messy to do asynchronous stuff in Wolfram. This is the Wolfram language. I like it because I can do all these interactive plots, plus it's very nice for mathematical code. Same signature, binary function, initial state, give it an observable, and you get a new observable. What's an observable? If you remember Rx, an observable is a gadget where you subscribe an observer. It's a representation of asynchronous data. An observer is a callback, but the abstraction of it is exactly the same as a list or as a stream. What fold observable does is take a binary function, an initial state, an old observable, and it gives you a new observable. You subscribe to that observable and you get updates. And that's exactly what I'm doing in the second line there. I implement all my functional operators over observables just as I implement them over lists. So in this middle bar here, I have harvest, which is my way of converting an observable to a list. So I just sit there and listen to it and reel it all in. I take observable, a fold observable. Look, there's my Fibonacci combiner. There's my initial state. There's integers from observable, another little thing on the side. But the point is, I can get Fibonacci numbers from lists, from streams, and from observables. So Kalman filtering is this fold, back to the meat, back to the combination of hammer and screwdriver. Kalman takes 2 inputs, a current observation and a model, and the current uncertainty and estimate of the state, and it spits out a new estimate and uncertainty in a state. And it's just another way, that cartoon is another way of representing this cartoon. Did the coefficients of polynomial. Let me talk about how we actually do this with the Kalman filter. So remember, this matrix on the left here is my matrix of models. Each line here is just t cubed, t squared, t1, t to the power 0. And here are my unknown coefficients. I multiply that big stack of models times my unknown coefficients, and I subtract the actual data. These are the times, and these are my noisy data. Of course, I can't do this. This isn't a numerical computation yet, but it will be in a second. Here's another way of representing that computation. I have the unknowns here. I have this big stack of data, and you can imagine what this is like when you have 250,000 orbital elements for objects in the solar system. It's not so funny anymore. So I'm going to make it funny. Here's the observations, the actual observations, and these are the residuals that include the unknown. And the way you do this with batch linear regression, or if you're doing a school exercise, is you take this giant matrix, you transpose it, and you have another giant matrix, and you multiply the two, and you get something that you can handle. So there's a little thing that you can handle way down on the left. You still have these pesky unknowns in there, but almost all the time you can invert that matrix. Bad practice, by the way, don't invert matrices. But if you had to, you could. And now On the right-hand side, we have concrete numbers, my actual observations. I have the inverse of this little matrix, model matrix, or model matrix times its transpose. And I get out my estimate of parameters. That's how batch least squares works. What is Kalman? And here's just another way of doing it. By the way, if you ever have trouble with algebra, draw cartoons. You don't want to see the messy notebooks that I filled up working out all of this algebra, but I did it all with cartoons. It helps it make sense. Above is the algebraic representation of exactly the same thing. Now, this is what I showed you before. Inverse of ATA times ATZ gives me my estimates. And the covariance, I could get the covariance also. Kalman must reproduce this. It's a unit test. I don't have types. Kalman works its magic like this. It does it one row at a time. I take one observation. I take one row. I put it in there. I multiply it by this magical thing called a Kalman gain. I'm going to tell you how that works. And for that, I'm going to go to Python. So just so you don't think that I'm doing Wolfram all the time. The Kalman gain, the magical Kalman thing looks like this. The new estimate is the old estimate plus a correction. That makes sense. We're updating. The correction is a gain times a residual. The residual is my actual observation minus my modeled observation. How do I compute the model observation? I take the model, which is deterministic, and multiply it by the old estimate. The old estimate is called x2 here for other reasons. So that's it. What does this gain look like? Oops. This is where it gets really cool. I know about 6 ways of deriving this gain. None of them are satisfactory. I've written a lot of them down. There's no way to go over them in an hour. I can't, one of these days I will find a nice way of proving this. In your mind, make the A's go away. All they do is translate from the observation space back from the units of measure of the observations back to the units of measure of the state. Remember, the gain is multiplying a residual. The residual is in the units of measure of the observations. And then we're using the gain times that residual to update the state. So I need to convert from the units of measure of the residual, which is the same as the observations, to the units of measure of the state. That's all that the A is doing in here. The important part is the P, which is the covariance, which is the uncertainty in my current estimate of the state. If that covariance is very small, then K looks like 1 over Z. What is 1 over Z? That is 1 over the covariance of my observations. So when my certainty in the state is very large, when my uncertainty in the state is very small, P is very small, K looks like 1 over Z. It says, don't pay attention to the observations very much. My belief in the state is very strong because P is small. So take the observations and listen to them by an amount that's proportional to the uncertainty in the observation, 1 over the uncertainty, inversely proportional to the uncertainty in the observations. Conversely, if P is very large, then K looks like 1. It looks like P over P. And that says, my uncertainty in the state estimate is very large. Don't believe my states. Listen to the observations. Listen to the residuals. It's K times the residual. OK, one last application. This is a really beautiful one. Let's consider the problem of a springy dumbbell. This is also called a dashpot. It's an amazing little gadget. I have seen gaming engines and physics engines for games that are built entirely out of this dashpot. I spent years working on tires for racing car simulations. A tire is one of the most complicated objects in existence, and if you this is why racing simulators came out only decades after flight simulators. Flying is easy compared to twisting a tire on the tarmac. Amazingly enough, you can build a model of a tire out of a truss of dashpots, and you can fool a Formula One driver with it. I did it when I was working on Forza at Microsoft. Okay, a dashpot is a fairly simple object. I've got masses at the end of a massless rod. I have a spring connecting the masses. I have a damper that's resisting the motion. The faster the masses move, the more the damper resists. There are 8 parameters here. That's represented by this big psi on the left. Q is the current extension of the dashpot. Q dot is the speed with which that extension is changing. Theta is the angle of the dashpot with respect to the horizontal. Theta dot is the angular velocity. And then I have 4 parameters, m, k, nu, and l: mass, spring constant, damping constant, and resting length. Why is this an interesting problem? You know this trick that kids do with throwing bottles? They toss a bottle and it turns and then it lands straight up on a table. It's exactly this. You toss the bottle. It only works when the bottle is half empty or so. Immediately, they toss it with a high spinning speed. Immediately, the water goes to either end of the bottle. And like the ice skater throwing her arms out and slowing down, the bottle slows down. And plunk, it lands on the table. And then the water hammers down and anchors it to the table. It's a trick. It's a glorious trick. Let's see if we can model it with a springy dumbbell. Answer is, yes, we can. And we're going to do folds everywhere. Talk about folds. I distribute this along with the slides in the notes. The first thing we expect to see if our model is working right, so this is just integration of the physics. This is no Kalman filtering yet. I'll tell you what Kalman filtering we're going to do in just a second. But this little chart down at the bottom right is the interesting one. That's the spin speed. The first prediction of our physics is that when you toss the thing, it starts off spinning fast and it ends up spinning slow. That's exactly what it does. So we're on the right track. Now, to make a Kalman filter out of this thing, it's a nonlinear problem. There's lots of crunchy and very interesting math. I've not expanded these out. They're quite big. But the EKF, the Kalman filter, is almost exactly the same as we had before. Look, there's the gain. There's the update equation right here. I multiply k times the residual. And guess what? I can actually estimate all 8 of those parameters observing only the angle. This is synthetic data, but we did some experiments with high-speed videography. We throw the bottle, we measure only the angle at 4,000 frames a second, watch the bottle land, and can estimate the masses, the spring constant, the damping constant, the resting length, and everything else. So this, I've drawn the ground truth in here as well. Some of you who know this subject will notice that there's a little bias. This is estimating the extension length, observing only the angle. And it's a little bit biased. If this were a spacecraft application or something mission critical, I'd dig into that and figure it out. It's probably quantization error in an internal integrator. It estimates the speed of vibration pretty well. It does great on the angle. Of course, the angle is what we're observing. And it does a really good job on the rate of change of the angle, too. And then, amazingly enough, I even amazed myself. I didn't believe I'd get any data out of here about the masses, the spring constant, the damping constant, and the resting extension of the dashpot, but I did. And then I cross-verified this with Mathematica, and You can see even the bias is maintained there. So whatever this source of this bias, it's fundamental to the problem and not to the particular solution that I'm using. Okay, so just the last takeaways. Here's the landscape of fold. And remember, Kalman filter is just another one of these binary functions. Kalman filter fits in this little slot. Kalman filter will make it possible for you to estimate the parameters and states of arbitrary models in constant memory and very, very fast, just a few instructions. It's incredibly valuable for robotics, for economics, for embedded systems. All three of these domains of sequential data have exactly the same shape. The domain of lists is very friendly. You have all your lists in memory. You have visualizers, debuggers. You can do fold of anything, initial value. You can go from list to list. The domain of observables, that's our harsh asynchronous environments where we can't debug anything and we stay up all night reading logs, trying to figure out what went wrong. But if you can take your code from the friendly environment and stick it into the harsh environment without even recompiling it, this is a huge advantage. That's the advantage of functional form for these kind of problems. And then finally, the domain of streams is a very nice theoretical abstraction for asynchronous data. Quite beautiful to play around with as an intermediate ground between the friendly lists and the unfriendly observables. So that's all I have for you today.